Hey, this is Math 7, Unit 6, Lesson 9, dealing with negative numbers. So we're going to show that doing the same to each side works for negative numbers too in this lesson. All right, so we began first of all with the conversation with your classmates about which one doesn't belong. And so when you looked at these four different equations here, you might have looked at them and said, well, which ones are equal, which ones don't actually work, and so you might have seen some different things. Here, for example, negative 5 times a negative 3 actually equals a positive 15, and so that does work out there. Here you might notice that a 2 plus a negative 5 actually equals a negative 3, so negative 3 does equal 3. And over here, if you did 4 minus a negative 2, when you subtract a negative, that's the same as adding, and so that becomes addition there, that when you move things around, and that simply becomes a 6. So we have to have those being equal there, no problem. But this one, negative 3 times a negative 4 is a positive 12. And so this one actually is not true, and so you might have just said, well, that's not true because it doesn't work out. But you also might have noticed some other things based upon whether you're doing negative numbers or positive numbers. You know, these ones here are multiplying and these ones here are doing add and subtracting. So you figure out which one wasn't going to belong. So that's a conversation you have with your classmates. Now we look over here at the next set of questions and we have old and new ways to solve. And when we look here, kind of our old way of solving was looking at the equations and saying, well, what value would make this equation true? If I had something like an x plus 6 equals 4, what number could I put in this situation in order to get to a 4 as a final solution there? And so you might think through some various numbers. Obviously, I have a positive 6 here. I'm trying to get to a 4, so I'm going to need to decrease somehow. This 6 has to go down in value to a 4. So thinking about maybe like a number line, if you had a number line, you were over here to 0 or something like that, although I'm out of space already. Let's not make that a 0. Fun room. Let's put a 0 about here maybe, and we'll do a 1 and a 2 and a 3 and a 4 and a 5 and a 6. And I know I'm located over here at x plus 6, and I have to get down to a 4 over here. Here's a 4. So I'm here, and I need to get over there. So that's not even quite right, because 4 is there. Oh my goodness. What am I doing today? Isn't it fun to make mistakes? It sure is. All right, so here's a 4, so here's 6, and I have something plus 6 gets me to 4. So I got to go from here down to there and add that number there. So what am I going to add? I'm going to add a negative 2 to get to that point. Now I could solve that by subtracting 6 to both sides, and that goes away, and 4 and a negative 6 still becomes a negative 2. And so I could do it with an equation sign as well, sorry, x equals negative 2. So that works, or you think about what's missing. Couple ways of going about it, up to you. What do you see? What do you want to do? And that's what's kind of cool about equations, is you can approach it in different ways. So I'm going to show you how I approach them, okay, and then you might have your own way of approaching them, and that's just fine. So here we look at the second one. We have x minus a negative 4 equals a negative 6. Now my way of approaching this, when I do that, when I see subtracting a negative number, I convert that into an addition problem to x plus 4. Because when I subtract the negative, it's the same as becoming just a plus sign, equals a negative 6. That's how I do that there. Now, for me, now at this point, I would subtract a 4 from both sides, because I have plus 4, so I do a minus 4, but leave me with just an x, equals negative 6 and a negative 4. I'm going to combine those together, and I end up with a negative 10. Another way of looking at this same one here is I could say that x minus a negative 4 equals negative 6. And what I could do is I could say, well, instead of subtracting negative 4, I do the opposite. I will add negative 4 to both sides. And if you look at it, when I add negative 4 to both sides, isn't this right here the same thing I'm doing right there? Yep, it actually is. So I don't really need to do the conversion to positive there if I don't want to. I'm still going to do the same thing by doing the same to both sides. I still end up with x equals a negative 10. Okay? And you will have a homework problem like this tonight as well. So that's why I wanted to show you that one. You could do it this way or this way. It really doesn't matter, right? I'm doing the opposite sign from a minus whatever to add. I'm doing the same thing to both sides. I'm adding a negative 4, adding a negative 4, and that works over here. Here I'm subtracting a positive 4. but that's not really any different, right? Adding a negative 4 is the same as subtracting a positive 4. It's the same value because that's going to end up still with a negative 4. Looking at number 3, we have this 2 times x minus 1 equals negative 200. And again, I could start by taking a look at this, and probably for my case here I would divide both sides by 2 so that x minus 1 equals negative 100. I'm going to add 1 to both sides so that x is going to be equal to negative 99. So that one's a little tricky, just to make sure you know what to do. From negative 100, one larger is actually going to become negative 99. Be careful with your arithmetic there. And finally, number 4, 2x plus negative 3 equals negative 23. And so to solve, I'll add 3 to both sides. Sorry, well, I could do let's think of it this way. This is a plus minus 3. So what we're wanting to see with this lesson today is that I could do subtract a minus 3, subtract minus 3. Now again, if I subtract a minus 3, that's like adding, and so that becomes a negative 20 here. So it probably in this case here might be easier to think about this as being, adding or subtracting, just adding a positive 3, but it's the same idea. And so 2x is going to equal negative 20. Okay, you divide both sides by 2, and x equals negative 10. Right, so that works out okay. Realistically, when I do this one myself, if I had 2x plus a negative 3 equals negative 23, I would probably rewrite that myself as 2x minus 3 equals minus 23, and then I would add 3 to get the negative 22x. Okay, you get the same spot here and here. I just don't want to usually play with two signs. I'll turn two signs into one just to make it a little bit cleaner to look at. It's an extra step that you probably will do mental math later on, but that's just what I'm doing there. Let's look at the next side. Okay, this one's called Keeping It True. It says here are some equations that all have the same solution. All right, and we started here and it goes all the way down. Explain how you know that each equation has the same solution as the previous equation, and we want to pause for discussion before moving to the next question. So what they're saying is that if I start with x minus 6, I'm doing something to turn that into this equation there. On this side, we can tell that I am doing what? I'm subtracting 3. And over here, to go from there to there, what is negative 6 minus 3? Well, negative 6 minus 3 is going to be a negative 9. So that's what I'm doing on both sides. When I look at this one, I can see what's happening here is I'm basically taking my hanger and flipping it around. Imagine I had a hanger problem like this, and over here was a circle, and over here was a square and another square, and they were balanced, right? Well, if I take that same hanger and redraw it and draw the square here, and a square here, and a circle, nothing has really changed. I've just taken the hanger and flipped it over. And that's what's taking place here. I'm putting the 9 over to that side and the x minus 3 to that side. No change. But to go from here to here, this is a change. Notice you can tell what the change is. I'm multiplying everything by, multiply by negative 100. And when I do it to this side, they kept it outside the parentheses, but over here, a negative 9 times a negative 100 becomes a positive 900. Right, and that's the change that's happening from here to here. On this line, the only change that's taking place is we're changing the order here, the commutative property, the multiplication. Let's put the negative 100 on that side. This is staying the same. The next line, that's staying the same. And here, we're distributing. So that's the distributive property. Commutative. I always spell that word wrong. All right. So that's what's taking place there. Now the next thing says to work with a partner, and you want to start with an equation like negative 5 equals x, and you want to do the same thing to at least 3 times to make a new equation. So as an example, what you might do, and this is just my example, but you'll do it on your own, is let's say I add 4 to both sides. If I did that, I'd end up with right now negative 1 equals x plus 4. And let's say I multiplied everything by 2. 2 times negative 1 is negative 2. And here I can say this is equal to 2 times x plus 4 and do it with quantity like that. So that's one step, there's two steps. But at a third step, I could then switch things around, say negative 2 equals, maybe I distribute, I don't know, and we distribute out, and I do 2x plus 8. So that's a third way of doing it. So this equation is actually, if I worked it out, still equal to that, because I did the same thing to both sides all the way through. Okay, so kind of fun little activity to do with a partner. You make up a little equation, see if they can figure it out, and get back to your original set of numbers there. All right, so in summary, when we want to find a solution to an equation, sometimes we just think about what value in place the variable would make the equation true, and sometimes we perform the same operation on each side. All right, so sometimes, for example, subtract the same amount from each side or add the same amount each side, trying to keep the balance hangers going on there. Okay, so it works for negative numbers just as well as it works for positive numbers, not a problem, and so that worked out great. All right, so let's take a moment to look at our homework, and then we'll check that together. All right, so here's tonight's homework. First of all, we have to solve each equation. So let's see what we have here. So in this first one, we have 4x equals negative 28. To solve that, I'm going to divide both sides by 4. And so negative 28 divided by negative 4 tells me that x is going to be equal to negative 7. And that becomes my solution there. For b, I have x minus a negative 6 equals a negative 2. Now again, this is one where I can add the same number, right? I could do plus a minus 6 plus a minus 6 here, right? That would work. Myself, what I would probably do is I would turn a minus into plus, and I'd probably write the whole thing over as x plus 6 equals negative 2, in which case I'm subtracting 6 from both sides. Now when I do this, is there any real difference here? This is eliminated, and I'm left with x equals a negative 2 and a negative 6 together form a negative 8. Here, that's eliminated, and x is equal to a negative 2 minus 6 is still going to be a negative 8. So you get the same solution, just a different way of approaching it, right? For c, we have negative x plus 4 equals negative 9. So I'm going to subtract 4 from both sides. So negative x equals negative, in this case here, negative 13. All right. Now I don't want to have a variable to be a negative. So what I could do is I can multiply, like we did in the problem. We made up your own problems, right? You made it a little longer by doing 3 things to it. I can multiply both sides by a negative 1, and a negative 1x, a negative 1 times a negative x becomes a positive x, and a negative 13 times a negative 1 becomes a positive 13. As long as I do it to both sides, I'm going to be okay. So a was equal to negative 7, b was equal to negative 8, c is equal to positive 13. For d, we have negative 3x plus 7 equals 1. I'm going to subtract 7 from both sides, so negative 3 x equals negative 6. Divide both sides by negative 3. So you have x equals to negative 6 divided by negative 3 is a positive 2. And then finally our last one, we have 25x plus negative 11 equals a negative 86. And so to solve this one here, what we would say is we would say we're going to go ahead and I'm going to go ahead and rewrite it this my way. 25x minus 11 equals negative 86. Then I'll add 11 to both sides. So 25x equals, in this case here, 75. Negative 75, sorry. Divide both sides by 25, so that x equals a negative 3. So lots of work there, lots of practice, but it's good practice to be able to do that again and again to make sure you're getting it right. Number 2, here's an equation. 2x plus 9 equals negative 15. Write 3 different equations that have the same solution as that one. So what that means is we take 2x plus 9 equals negative 15, and we're going to do something to both sides to make it a new equation, but still be pretty much the same. So let's say I subtracted 9 from both sides. Fair enough. We'd have 2x equals negative 24. That's still exactly the same. There's one equation. Let's do another one. 2x plus 9 equals negative 15. What else could I do? I can add 3 to both sides. Does that do anything? Nope. I get 2x plus 12 equals negative 15 plus a 3 is a negative 12. Is there anything wrong with that? Nope. It's another equation. So there's 1, there's 2, and I'll let you make up one more. It's up to you. Okay, number 3, a little tape diagram, selecting all the equations that match that diagram. So here we have 18 as my total, and that's going to be equal to, I have x plus 5 there, that's what's inside the box, and there are 3 of them. So that's my basic equation like that. In terms of things I could do with this, right, we could distribute that out. I could write this as 18 equals 3x plus 15. That could work. I could get the 3 on the other side by doing 18 equals 3 times x plus 5. To get the 3 on the other side, I can either think about it as being divided by 3, right? Or I could think about it being 18 equals 3 times x plus 5. Oh, sorry, I'm really messy. I could think about it as 18 equals 3 times x plus 5. If I multiply both sides by a third, that's the same as dividing by 3. That works as well. And then when you do that, you end up with an answer like 6 equals x plus 5. So that's also the same. And technically, if I subtract 5, I can have 1 equals x, and that's still the same. But let's look at our choices. That's a lot of stuff there. Here we have x plus 5 equals 18. That's not true because that's only one of them, so it's not possible. Here, 18 divided by 3 equals x plus 5. Well, that's the x plus 5 quantity, and we divide it into 3 sections. And that's really what we're doing, isn't it? Here we're taking this and we're dividing the 18 into 3 sections. And when we divide 18 by 3, what's inside of them is x plus 5. And we can see that's actually happening right here as well. If we completed that one out, we have 18 divided by 3 is equal to x plus 5. That's going to be great. Here is 3 times the quantity x plus 5 equals 18. That's the same thing there. Now for D, we have x plus 5 equals 1/3 times 18. Well, that's what we have here. This is 18 times a third. This 3 cancels out with that 1/3, and so that matches. And this one here does not. This is just combining the 3 x's here, here, and here the wrong way. So that's not going to be proper. Next page, number 4. Match each equation to the story. And we have, first of all, a stack of nested paper cups is 8 inches tall. The first cup is 4 inches tall, and each of the rest adds 1/4 inch to them. We don't know how many, so we can call how many there are x. So we know we're going to have in total a stack that's 8 inches tall. So my choice is going to be here or here. Because the first cup is 4 inches tall, then I know I need to have just a solid 4 to start with, and then we're going to add 1/4 of an inch for every cup. So number 2 matches with A. The next one says a baker uses 4 cups of flour. That's probably in my total. So when I look at my total choices, I have 8 and 4. Probably going to go with this one, but let's keep reading. She uses a 1/4 cup to flour the counters. Well, there's a 1/4 cup to flour the counters, and the rest to make 8 identical muffins. We don't know what's left, but she makes 8 identical muffins with whatever's left. So 3 is going to match B. And finally, Elena has an 8-foot piece of ribbon. She cuts off a piece that is 1/4 of a foot long, right? So here's 8, and so we're going to cut that into 1/4 inch there. And then she cuts the remainder into 4 pieces of equal length, right? This is a great one to think about as a tape diagram, right? So if you have your length, and we know we have 8 here, she cuts off a piece that's 1/4 inch long. There's 1/4. And whatever's left, she cuts into 4 equal pieces, 4 pieces equal length. So we have 1, 2, 3, 4, and they're all the same. Right? By writing it that way, you can tell that what do I have? I have 1/4 plus 1, 2, 3, 4 x's is equal to 8. And this is why we do the tape diagram. Sometimes it's easy to take a look at a problem like this and draw it off as a tape diagram and be able to recognize in the tape diagram what the equation could be. And that's the whole purpose of doing it that way. So that's what we got. And finally, number 5, it says there are 88 seats in the theater. The seating in the theater is split into 4 identical sections. Each section has 14 red and some blue. So sum's X there. So tape diagram looks something like this, right? We know that there are 88 seats in the theater. We know we're in 4 sections. There's my 4 sections. And each section has 14 red and some blue. So 14 plus X, 14 plus X, 14 plus X, and 14 plus X. That's what we know. What unknown amounts can be found by using the diagram or reasoning about this section? Okay, so what could we find out? We could find out the number of blue seats in a section, right? We could solve it and solve for X. We could do a number of blue seats total, because once you find an X, if you add all the X's together, that gets you a total. We can find out the number of red seats total by multiplying 14 times 4. That's another thing we could do there. Yeah, so those are just some ideas of what we could do. We could also do the number of seats in a section by solving that out there. So there's a couple options we could do. And so if you have the problem out, you do 88 equals 4 times 14 plus X. So if we divide both sides by 4, you end up with 22 equals 14 plus X. So the number of seats in a section is 22. Do we know how many red seats there are? We know there's 14 red seats already in 4 sections. So if we did 14 times 4, we'd end up with 56 red seats in total. In terms of blue seats, if we subtract 14, we end up with 8. That means there's 8 in one section, but since there's 4 sections, 8 times 4 is 32. And does that combine to give me 88? It sure does in total there. So lots of things you can find out with just that little picture and tape diagram. That's it for today, and we'll see you next time.